Welcome to RedisConf. My name is Taimur Rashid. I'm the Chief Business Development Officer here at Redis Labs. To build on the theme of rediscovering the power of real-time data, I'd like to share with you how Redis can be used as an online feature store for machine learning use cases. I'll also be joined by Dvir, my colleague, who will actually lead a technical discussion and show a demo. Today's agenda is as follows. We'll talk about the data challenge that exists in operationalizing machine learning. As part of that, we'll actually share what this emerging data architecture is with the feature store and actually show how Redis can be used in that context. Dvir will lead the technical discussion and the demo. We'll share some performance benchmarks regarding Redis, go through a fraud detection example, and then hopefully end with some key takeaways. A little bit about me. So I've been with Redis Labs for 2 months. I'm leading business development efforts here with a specific focus on machine learning and artificial intelligence. Well, let's talk about the data problem that exists with operationalizing machine learning. What we've noticed is that analytics data is mostly confined in batch processing. And when it comes to machine learning use cases, you actually need to combine batch and real-time data. Now, data scientists actually need a feature pipeline to create features, manage them, and serve them. And while many data scientists do this today, oftentimes it can be a bit siloed, there can be duplication of features, and the overall process has a number of inefficiencies associated with it. This can get really complex, and at the same time, as you try to bridge the feature data with the models, you need to ensure that you have consistency across the organization. Feature stores is what is emerging within the overall data architecture in machine learning. And much of this is coming from very big companies that have built machine learning platforms at scale and them sharing their reference architectures, learnings, and approaches. So what is a feature store? A feature store is essentially a bridge between your data and your machine learning models. And when you actually look at the data, it is the feature data. It allows teams to register, ingest, serve, and monitor features in production. Now, feature stores have two aspects to them. One is data orchestration. You can think of these as tools that effectively give data scientists the ability to create features, do the necessary transformations with them, share them, build them into their models, and then over time refine the definition of these features. Then you have data serving, which is how you actually serve those features in the actual model. And this requires low latency serving and low latency inference. The benefits of the feature store are fairly clear. On the data orchestration side, you get version controlled way of managing features. You have a process through which you can curate them, you can share them. You effectively bridge a gap that exists between data scientists and machine learning engineers. Given the fact that now you have a single way and a single process for taking raw data, defining features, and then building them into the models, you effectively have a very good data lineage posture. On the data serving side, you ensure that you have parity between online storage and offline storage. You can serve features in a batch mode, in real-time capability. And one of the biggest benefits that you get is you can actually monitor the overall model performance and the data performance to really see, is there any drift in your model? Is there any drift in your data? And this effectively helps you improve the accuracy of your models so that over time you can really truly get the benefit of machine learning. Now, there is a thing to consider with latency of data. And this really defines what use cases are requiring real-time capabilities versus batch capabilities. And what you have here on the left-hand side is a continuum of low latency data and high latency data. You can think of low latency use cases such as fraud detection, online predictions, cybersecurity, which require very, very fast response times and the ability to calculate features and serve them into the model so you can get a very accurate and timely prediction. But at the same time, there's certain use cases that don't require that real-time nature, and therefore have different latency requirements. But effectively, once you've identified the universe of your data, you effectively feed that through a feature pipeline, which does the necessary transformations. When you finally have that, you can store data into a feature store. Now, as I mentioned, there are two aspects of the feature store. Data orchestration, which is really about feature management, the training process, the governance associated with the features that you've defined. The second aspect is data serving. So where do you actually store the features when you're going in production? How do you serve them? And then ultimately, how do you monitor the effectiveness of them? This is where if we took that canonical feature store, what we actually see is that it's a dual database. On one hand, you have an offline feature store, which is optimized for training and batch processing. Then you have the online feature store, which is really serving in real time and doing the inferencing capability in an online fashion. And when you have the monitoring capabilities, you can effectively close the loop in seeing how do you update the online store with new feature information, or how do you actually take that new feature information and then retrain the model. Now, where does Redis fit? Redis is actually fitting in the online feature store capability. When you actually look at it, customers are taking Redis standalone and building the necessary capabilities around it to effectively have that online feature store. When you combine Redis AI, which is a module that brings inferencing closer to the data, you effectively augment your online feature store with feature serving capability as well as feature monitoring capability. Now, when you look at data orchestration, what are some options there? One of the options that I wanted to highlight is Feast. Feast is an open source feature store machine learning software. It supports batch and streaming data sources, and given that it uses Redis as an online store, you can effectively use it for real-time use cases as well. And it's available for download at feast.dev. And we've been working very closely with the Feast team to expand the integration and the feature set as it relates to Redis and the Redis modules. Now what I'd like to do is I'd like to turn it over to Dvir, who's actually going to lead a technical discussion looking at Feast and Redis together combined, and he'll actually also show a demonstration as well too. So over to you, Dvir.
Thank you, Taimur. Hi, I'm Dvir. In the last 2 years, I've been part of Redis Labs CTO office, or the Redis Labs incubation team. I was working on Redis Graph and recently started working on Redis AI and other machine learning related projects. Today, I'm going to talk about expanding the capabilities of your feature store with Redis AI and Redis Gears. So the idea of having a dedicated component for data serving in your machine learning pipeline is excellent. It allows you to keep your data teams focused and provides a one-stop shop for your organization data requirements in the different machine learning pipelines. All this while maintaining modularity and isolation between the pipeline's different components. So one can argue that feature stores are limited or limiting themselves to only provide data serving and orchestrating. By itself, it is a great achievement and a valuable key component in the modern machine learning pipeline. But is it enough? Moreover, since the domain is not standardized yet, each feature store provider or even a homemade feature store use their own proprietary data formatting and abstractions. So let's first discuss about the data formatting and abstractions, and we take Feast as our feature store of reference. Each data point in Feast or data row is stored as a Redis hash. The key name is a combination of the row identifiers, unique identifiers values, and we got a 32-bit hash function that manipulates the hash field names. The values themselves are kept in a serialized Feast proprietary protobuf format. Now let's see a complete inference flow. Assume that I'm using Feast as my online feature store and I'm using Redis as the storage behind the scene. Assume that I have a Fist Python client, a machine learning model running in my application. This application requires the data in Fist to run the inference on. My application issues a request to Fist. Fist then will use its knowledge about the data abstraction, the key name, and the field names to send Redis the right request. Redis in turn will return the data to Fist. The Fist will use its knowledge about the data format to process the data and return the required response. Overall, I needed 4 hops between different applications or different machines to run the entire process. Now, let's see how we can overcome some of the limitations that we showed earlier. For once, we can allow in-process inference with Redis AI. This can save us some precious time spent on the network and applications communications. Also, we can distribute some of the knowledge about the data format and abstractions to Redis gears to help transform proprietary data abstractions into Redis AI uniform tensors. So in the following demo, I will be using Fist for storing our features, and Redis. This Redis will be packed with Redis gears and Redis AI loaded with a machine learning model. We show that by distributing the knowledge about data abstraction and format to the different components in the inference pipeline, we can reduce the number of hops in the inference process. So I wrote a simple Python client in my Jupyter notebook that is aware of the Fist data abstraction, meaning it knows about using hashes and it knows about how key names and field names are generated. This client will trigger Redis gears execution, which in turn is aware about Fist values data formatting, meaning it knows how to convert the serialized protobuf array into Redis AI uniform tensors. From here, I will just call Redis AI from within Redis gears to run the model and return the data. So let's continue to the demo. So welcome to my Jupyter notebook window. In this demo, we're going to see the implementation of the previous slide that we just saw. For convenience, everything is already preloaded into Fist and Redis, so we can just start our discussion. So our data is the following data frame that consists of 2 rows. Our schema has only 2 features, A and B, and a unique identifier, which is the row ID. For the first row, the unique identifier equals 1, and the feature values are both 2. And the second row, the row identifier is 2, and the feature values are both 3. Now, let's see how the data comes back from Fist by issuing a get online features request. We can see that for demo table A, we get the values 2 and 3 as we can see here. And for demo table B, we can see we also get the values 2 and 3 and the row identifiers. The model that I use is a simple TensorFlow model already loaded in Redis AI that just calculates a simple multiplication of the values A times B and returns it as a C. Now for the client-side data abstraction. Here I have defined a simple function that naively tries to implement Fist data abstraction with respect to hash key name and field names. For the key name, we just using the combinations of the entity unique identifiers, name and value. And for the field names, we just applied a 32-bit hash function over the required field names. In the following script, which is submitted to Redis gears, I have implemented a transformation. This transformation takes a raw Fist value format as stored in Redis and transform it into Redis AI tensor. This is done by simply providing the script with Fist value protobuf definition. This will allow the script to create and parse those values from within the script. So basically what this script does is just extract the feast values by using agent get from the key and fields sent by the client and pass it from the raw data buffer. Then we're going to transform them into tensors by applying the feast value to tensor function. We just create a tensor from a value. Here, the value is already a feast value object that was decoded by Redis Gears itself. From here, now that I have Redis AI tensors, the way to run the inference is very, very short, and I will not delay on this part of code over here, which is a normal Redis AI API within Redis Gears. So let's put it all together. Recall our data. We got two rows. The first row has two values of 2, and the second row has two values of 3. Now, here, this is what the actual inference process looks like. We're going to have to generate the parameters for each data row, and then we're going to trigger the script that we just saw in Redis Gears to run the inference. Here we have already pre-calculated results, but let's run it now, and we get that 2 times 2 equals 4, and 3 times 3 equals 9. So this summarizes the slide that we showed earlier, that we can reduce the number of hops by allowing both the client and the Redis Gears to have some knowledge about how your data is abstracted and formatted. So this concludes the demo, and I pass this session back to Taimur. Thank you very much.
Thank you, Dvir, for leading that technical discussion and showing the demo for how Feast and Redis can be used. Now, to build on what Dvir just mentioned, I want to show you how you can expand the online feature store capabilities with Redis AI and Redis Gears. Now, when you actually look at this table here, you can see that Redis standalone, you can take it today and effectively use it as an online feature store with the Feast support there as well. Now, if you wanted to actually enable feature serving, feature monitoring, and to an extent use Redis as a model store or a model serving solution, this is where you can use Redis AI to get those capabilities. And then if you wanted to sync with an offline store, you can leverage Redis Gears in that process to get the full set of capabilities. And what this shows you is that with Redis, you can get a full solution for an online feature store by leveraging these capabilities. If we look at the throughput benchmark, you can clearly see here how Redis AI performs extremely well compared to TorchServe, TensorFlow, or even a common HTTP server. In the context of latency, you can also see that Redis AI is far lower, which is better than the other comparative solutions such as TorchServe, TensorFlow, and a common HTTP server. When we actually look at the overall value prop of Redis AI, it makes AI simpler and faster. When you look at the left-hand side and see how an online feature store can be used, it's typically very complex and slow. You can see the number of hops here between the app servers, the database, and the AI processing capabilities. You're looking somewhere between tens to hundreds of milliseconds. Now, when you build your online feature store with Redis and Redis AI, you can clearly see that the architecture is far simpler. The number of hops is reduced, and you get 10 milliseconds and even less based on your use case and how you optimize the overall architecture. Now, in an example with fraud detection using Kaggle's credit card fraud detection, you can see this play out in the very same way. On the left-hand side, you have model inferencing with Redis as a feature store. And you can still see that it's a fairly decent architecture with a number of hops between the application, the store itself, and then the actual model that's built on Kaggle. But on the right-hand side, you can see with model inferencing with Redis as a feature store and Redis AI, your architecture is far simplified, and we have seen anywhere from 10 to 100x improvement in the overall response time for this specific use case. So to sum up, the feature store is a bridge between machine learning data and models. And whether that data is your features or it's actually a model that you're storing in Redis as a model store, this is effectively helping many of our customers with the ability to get the value of AI and machine learning. Now, feature stores encompass data orchestration and data serving. Redis can be used as that online feature store. With Redis AI, you can bring inferencing much closer to the feature store and effectively get lower latency feature serving and monitoring. And then finally, if you choose to, you can sync with an offline store by using Redis Gears. I want to thank you all for the time here. Hopefully you found this presentation beneficial. We are still in the early days of what we can do here, but this is where we are today and we'll continue to build on this. I've referenced a number of resources here that I encourage you to take a look at. Reach out to us if you have a machine learning project and you want to see how you can use Redis and rediscover it for those use cases. Our email addresses are here and we'd be happy to support you through that effort. Once again, thank you, and we hope you enjoy the rest of RedisConf. Bye-bye.